As the FAA works to integrate drones into the national airspace, maintaining separation between manned aircraft and drones is essential. This is an example of what could possibly happen if a drone were to impact a commercial aircraft. There hasn't been much work done to study the potential impact forces that exist between a drone and an aircraft.
Currently, the Composite Technologies Research Group is using a launcher to fire drones into sheets of plywood to study the potential impact effects. Currently, the launcher is capable of approaching speeds of up to 180 miles per hour. Dr. Cairns tasked our team with developing a panel for the drone to hit that is able to measure the associated impact forces versus time.
This is the design we came up with for the impact panel.
It is made out of ASTM A514 steel and is 1/4 inch thick.
This pad needs to be able to withstand an impact of a 10-pound drone traveling at 250 knots.
The brackets are adjustable so that several different wings can be mounted.
The panel itself was tested in an ANSYS explicit dynamic simulation to gain an understanding of the stresses and deformations that the panel would experience when being hit by a 10-pound drone traveling at 250 knots.
This is the von Mises stress for the worst-case loading situation.
The panel experiences slight yielding, particularly around the bolt holes, but catastrophic failure is avoided. The simulation occurs over a timescale of 3 milliseconds.
This is the deflection for the worst-case loading situation.
Although a nearly 2-inch deflection represents the potential for measurement error, this panel was accepted because it offered a good balance between weight and strength.
This is the stress and deflection for a normal load, which is a 5-pound drone at 180 miles per hour. This supports decreased deflection but adds stress.
This is the final design, including the stand and panel. It supports normal impacts anywhere on the panel, and worst case loading as long as you hit it close to the center. The panel will be connected to the stand using load cells to properly measure impact forces. We also completed a finite element analysis of the stand. Here is the code.
The code works by treating each piece in the stand as a beam element with 2 nodes. Each node has 6 degrees of freedom. It assembles the global stiffness matrix for the stand and solves for all unknown nodal loads and displacements. Using geometric and material information, the code then solves for the equivalent stress within each piece of the stand. Running the FEA solver with inputs for the stand under the worst-case loading situation returns a maximum von Mises stress of 43,617 psi, a maximum displacement of 0.11 inches, and a maximum nodal load of 4,593 pounds.
As for the stand, the factors of safety for buckling is 3, yielding is 1.2, and the Unistruct guarantee is 1.67.
The panel, frame, and stand have a conservative service life of 1,000 hits. It is recommended that the assembly be inspected after each testing session. If a severely off-center hit occurs, the assembly must be inspected for damage before testing can continue. For project management, the team communicated through group text. The group chairman was rotated every quarter of the semester, and they were responsible for submitting deliverables. Every team member had discretion over what they needed to do. Next semester, the chairman will be rotated on the same schedule. Shop time will be scheduled as early as possible to ensure that manufacturing goes smoothly.